Good morning, everyone, and thank you for joining us for the 42nd webinar of the Offshore Wind series, Learning from the Expert. I'm Pauline Hewitt-Lebertry. I'm Assistant Director of nyserda's Offshore Wind team, and it is my pleasure to be joined by today's expert, Dr. Eric Hines from Tufts University and Dr. Simon Watson from TU Delft. Before introducing Eric and Simon, a few reminders for participants and some background on this webinar series. So, next slide, please. Thank you. Firstly, if you're experiencing any technical issues, please contact Sal Graven at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Expert series are available on nyserda's website at the address on this slide. All participants have been muted. We will have a time for Q&A following the presentation, so please use the Q&A function to submit your question for the speakers. Next slide, please. Thank you. So New York is working to advance the responsible and cost-effective development of at least 9,000 megawatt of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goal of 70% renewable sources of electricity by 2030 and 100% zero emissions electricity by 2040. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders, and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore winds. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic of speaker for a future webinar, you can email us at offshore-nyserda.ny.gov or fill out our survey, also available on our website, nyserda.ny.gov, Offshore Wind Webinar Series. Please note that the views and opinions expressed in these presentations are those of the presenters. So, it is my pleasure to introduce our speakers. Dr. Eric Hines directs the Offshore Wind Energy Graduate Program at Tufts University and has over 25 years of experience engineering innovative infrastructure. He works at the Technology Policy Interface to develop system-level design concepts and has received numerous awards for his work in industry-driven research. Dr. Simon Watson has worked in wind energy since 1990, starting at the Rutherford Appleton Laboratory in the UK, and since 2017, he has held the position of Professor of Wind Energy System and Director of the TU Delft Wind Energy Institute in the Netherlands. His areas of research include wind resource, wind farm aerodynamics, wind turbine reliability, and condition monitoring. Professor Watson is the current editor-in-chief of the Wind Energy Journal. So today we're departing a little bit from the typical format of this webinar series, and we will begin with a question for our two experts. How does offshore wind research and development contribute to new technology? And why is continued R&D important for offshore wind? Simon, can we start with you, please?
Sure, thanks very much for the introduction, Pauline. Obviously one of the key drivers has been to try and reduce cost. When offshore wind was first being developed, particularly in Europe, then you were looking at the cost of the electricity being several times what it is onshore. So R&D has very much helped to drive down the cost. Not the only factor, of course, but it has been an important factor in terms of reducing that cost. So we're now at levels which are without requirement for subsidy. We're now moving to a situation where it's not just about reducing the cost, but also about adding to the value of the energy that's produced by the wind turbines, the energy and the power, of course, because as we go to have more and more of the power generated from renewables, particularly offshore wind, then the power needs to be more dispatchable. So we're looking at solutions now to do that, and that's where R&D, I think, is very important. It's also about reducing the risk, of course. In order to build offshore wind farms, then there are lots of risks associated with that, and that's been part of the reason that it's been so expensive, of course, in the early days. And R&D can help reduce the risks. It can help reduce conservativeness in designs of wind turbines for the offshore environment. And what's something which is very important now, particularly in Europe, is reducing the impact on the environment. The developers, the OEMs, are obviously very much focused on delivering the technology, putting it out in the sea. But of course, we know that if we're going to effectively industrialize our offshore areas, that will have an impact, or potentially can have an impact on the environment. And that's where research can play a role in terms of reducing that impact, mitigating that impact. We have big targets, of course, for the build out of offshore wind to meet the net zero requirements across the world, certainly in Europe, and that requires a huge scale up. I'll kind of touch on that a little bit later. And of course, in order to satisfy that scale up, we do need new innovations in terms of turbine design, in terms of installation, operations, maintenance, and ultimately, of course, decommissioning. We're moving to larger machines, and that represents challenges where we're using design codes that were developed for machines which were perhaps much smaller than they are now, and we have to think about R&D to develop new models that can actually properly capture the behavior of the turbine, so we can actually, again, reduce conservativeness in designs. And we need to make sure that the machines are more flexible in terms of how they operate to meet the requirements of the grid for things like grid forming, providing ancillary services to the grid, and that still requires a lot of research. So those are a few of my thoughts, and I guess, Eric, you've probably got some ideas of your own as to why R&D is important.
Yes, thank you, Simon. Thank you, Pauline. I mean, Simon, I think you've outlined very well the major themes in offshore wind R&D research. And of course, for everyone here on the webinar, Simon's institution is at the center of a lot of these research efforts in Europe. And I would encourage everyone to really be curious and educate themselves about what's going on in Europe and where the Europeans are now in the industry. There's a lot that we can learn in the US from that experience. So when I think about offshore wind research, I think about scale, and the scale of offshore wind can truly be hard to imagine. Projects cost billions of dollars. We talk about this, easily and freely nowadays, but billions of dollars are a lot of money. And their timelines from conception to commercial operation extend over 10 years or more. Once completed, these projects have to function reliably and consistently for several decades. And so with so much at stake, it's critical to make choices based on tried and true experience. So while the way things were done last time almost always leaves room for improvement, it's often too risky to try new things in a given project. And this is really where research comes in. And so with the development of a new technology, we have to expect that there will be failures and that these failures will lead to opportunities for us to learn. So new technology needs safe and creative spaces for exploration and experimentation. Projects, on the other hand, need to be delivered, they need to be reliable, they need to be guaranteed, and they need to be on time. These are different spaces for different activities that ultimately come together to create a thriving industry. The cutting edge of US R&D is to connect the social and technological challenges of individual projects with R&D communities that can work collaboratively to address these challenges systematically over time, over several projects in a longitudinal manner. R&D spaces must be designed to allow people to speak freely, unconstrained by project, financial, and political commitments. So we have to have spaces where we can work creatively so that we can advance the projects that we're trying to build. And R&D is important for offshore wind because we have big questions that we need to answer. And you heard this in Simon's comments. In order to deliver a just energy transition, how do we create high quality jobs for a wide range of people? We have many choices in front of us in terms of how we decide to build this industry. How do we revive the health of our oceans? They're ailing. And we can use offshore wind as an opportunity to actually make them healthier. How do we do that with nature inclusive design? And the Netherlands is one of the world leaders in this right now. And then how do we build our energy infrastructure to perform well for generations to come? so that what we're investing in now really does benefit our grandchildren and our great-grandchildren.
And maybe a point, I don't know how we're doing for time, Pauline, but another
Yes,
point to
yes,
make
you do.
is that I don't know, another point to make, and I'm
Yes,
not
go
quite
ahead.
sure whether the follow-up question to this is kind of like the future, isn't it? The future for requirements for R&D, and of course the scale up is a big issue. You know, as I think as Eric said, you know, it's very difficult to comprehend the scale of build out that we need for the technology, and that's only going to happen if we have, you know, the R&D there, and also we're going to be moving to deeper and deeper waters, further away from the shore, hundreds of kilometers away from the shore. That's a huge technological challenge in terms of how you build, how you maintain, how you operate, and ultimately how you decommission the wind farms.
We have a few more minutes, Eric, if you want to add something, because this is a great conversation before your presentation, if you want to add anything.
Well, I guess I would add our experience. You know, the United States, we've been at this for over 20 years now. And I would say that even though the Europeans encouraged us to learn as much as we could, you know, from their experience, because they learned everything the hard way, and as our colleagues have said, you know, some of the mistakes they've made them more than once just to make sure they were mistakes. We've done the same thing. And I think this is important to recognize. We've learned a lot of things the hard way. And it's understandable because we're actually dealing again with these incredibly large systems that touch almost every aspect of our lives and every aspect of society. This is not an industry where you can just create a technology and suddenly solve the problem. This is an industry where technology is essential for problem solving, but it has to be integrated and embedded into social, political, economic, and cultural frameworks, really in individual specific cities. And so what happens in one city may be similar to what happens in another city, but it will also have its own character. And embedding this in context and truly understanding the role of technology in context is critical in this case. And so I would say this is an opportunity, and I think a lot of us are drawn to this field because it's an opportunity to work across multiple disciplines with our colleagues in the humanities, to work on issues of social justice, to work on issues of policy. And these are areas that traditionally have been able to get along fairly well on their own without deep, intensive interaction. Offshore wind changes that. It's a game changer from a societal point of view, and I think it really clarifies what's at stake and the challenges that we face in the energy transition. So it's extremely useful in that way for helping people understand what we have to do to save the planet.
Thank you very much to both of you. That was a great introduction to your presentation. So now that you are both going to provide a case study to examine some of the biggest research problems we face in offshore wind and how your programs are approaching those issues. Eric, we will begin with you, if that's okay.
Thank you. Sure. All right, so we can advance to the next slide. This is an old slide now. Kind of astounding how quickly time moves on. But this was a moment in time where over 5 years, the size of the turbines increased by more than a factor of 3 and the cost decreased by a factor of 3. And apologies to my New York audience for showing Boston buildings here, but this is how we get a sense of scale. So we'll move to the next slide. This is a report that also came out now 5 years ago from the IEA that there was enough offshore wind worldwide to power the entire world 11 times over in 2040. We have the resource, we have the technology, and this is all possible. The real essential question is a question of scale. So these two ideas really contextualize this historic moment that we're in and the challenges that we face. So next slide. Just as a general round number, I use this to try to help my students understand the energy transition because we have to speak in gigawatts and terawatt hours. The Biden-Harris administration created a goal of 30 gigawatts by 2030. The goal that we think is reasonable for offshore wind, the minimum goal for the US is 300 gigawatts by 2050. And that's 10% of what we need to build out for US wind and solar, approximately 3,000 gigawatts by 2050. That's 3 times the size of our current electricity generation capacity in the US. 300 gigawatts is over $1 trillion of investment, by the way. Okay, next slide. So just a little bit by way of introduction, how did we get involved in this at Tufts? In 2008, I was asked to help design the Wind Technology Testing Center, which became the largest wind turbine blade testing facility in the world at the time. This is just north of Boston. And in building this project and doing something unprecedented, we really encountered the kinds of issues that you encounter when you try to do something new in the context of an individual project. And you had better believe that there were actual research activities required in this project in order to build this center and to make it function. Next slide. Next slide, please. Shortly after that, the owner of the WTTC, as we call it, the Wind Technology Testing Center, the Massachusetts Clean Energy Center, was tasked with developing North America's first offshore wind logistics terminal. And I served Mass CEC as the owner's advisor on this project, and some of my colleagues and I were in charge of the design of this project. And this was another project that really helped us understand offshore wind and what was going to happen. Essentially, we're on a glacial moraine in New Bedford with a lot of boulders and a lot of bedrock. We're in a contaminated harbor that's an EPA Superfund site. And because of the Jones Act, we had to build a landside upland area and quayside that could support some of the largest crane loads in the world. And so these two infrastructure projects really conditioned our understanding of the offshore wind industry and what we would need. We would need a network of ports and a network of labs, all at this scale of $100 million plus facilities in order to be able to land this industry and grow it in the United States. Next slide. And so this is just a summary of that, in the 16 years of offshore wind innovation and research at Tufts, the first 8 years we really spent building the infrastructure. And then after that, and what we learned from that, we've started to build our research portfolio. And so I'll be explaining a little bit of that to you and explaining and sharing where we see the cutting edge. To the next slide, please. It's helpful to look at Europe and the US. When I make this comparison, I'm always surprised as an American how big the North Sea is. It's massive. It's quite shallow in comparison with the US East Coast. We do have an outer continental shelf, but you can see how shallow, you can see how thin it is compared to the areas in the North Sea. Also, the North Sea is set up in some ways to facilitate a natural electrical network, and it has an existing oil and gas industry. Where the US has deeper water, we're essentially on the East Coast, an area on the ocean that is focused on fishing and recreation for hundreds of years. We do not have an oil and gas industry on the East Coast. We do have hurricanes, we do have right whales, and all of our power is on one side of the coast, and we need to somehow transfer this power to the other side. And so if we pay attention to these big picture issues, you can understand a lot of the necessary research in offshore wind to make this thrive in the United States. Next slide. And so I will argue that we need a systems level approach. We need to build an infrastructure that can last for more than 100 years. We need to prioritize social and environmental justice when we build this infrastructure. We then need to think about our supply chain. There is a turbine installation vessels, and there's a global supply chain shortage. There is more demand for offshore wind right now than we have supply, which is why prices are going up. So we need to invest in our supply chain so that we can build the offshore wind and get prices back down. We need to leverage our existing assets, pivot them, move in a new direction. We need to create US jobs. And then finally, for transmission, we need to figure out how are we going to integrate 300 gigawatts of offshore wind, even along the Atlantic coast by 2050. And this brings up issues like the North American macro grid, which is going to be necessary for the energy transition. And I'll touch on that in a minute. Next slide, please. So I'll begin with infrastructure. How can we learn as much as possible from what we've built so far? We've built a few wind farms. This is the work we're doing on monitoring the Block Island wind farm in collaboration with the US Department of the Interior to learn as much as we can from our instruments of how do these wind turbines behave in US waters. And so far we've learned a lot. Next slide. If we think about infrastructure and we think about making it last, this is a bridge that I was involved in over 20 years ago and was in charge of the testing for at University of California, San Diego. You see the right-hand side, that's a 25% scale model of the piers that support the new San Francisco-Oakland Bay Bridge East Bay spans. This bridge was built to last for 150 years and to survive a 1,500-year earthquake on the San Andreas or Hayward faults. This is how we think about our infrastructure, and offshore wind is our energy infrastructure. We need to be building this infrastructure to last for generations to come. Next slide. There may be a delay I'm experiencing, so I hope it's not too disruptive for folks. This is the Hoover Dam. The Hoover Dam was built in the 1930s and is well over 80 years old. And I haven't heard any stories about anybody tearing this dam down anytime soon. These things, this is something that was built and has lasted for generations. Clearly, the history of dams in the United States is a difficult history. Socially and environmentally. It's problematic for a number of reasons, and we should be learning as much as we can from it. And we should also be learning about what it means for us when we build infrastructure and we begin to rely on it, that it's extremely important that we start to expect it to last. Next slide. So what would it look like? This is our imagination of a kind of an offshore wind foundation that could be built to last for 100 years, to mitigate wave loading, to be towed out by tugboats that do not need installation vessels, and that could actually grow artificial reefs through nature-inclusive design. These are low-carbon concrete foundations. They can be designed to be nature-inclusive, and they can provide the transition from fixed to floating infrastructure. This is not something that anybody would take lightly and just design on a new project, but if we're able to figure out how to demonstrate how these things work in the same way that we demonstrated with the WTTC and the Marine Commerce Terminal, that we can do new things, then we can start to change the way that this is done and actually develop foundations in the water that make the ocean healthier and that help our fisheries thrive. Next slide. Supply chain. What you see on the right is a graph that was developed by the National Renewable Energy Laboratory and was published in early 2023, where it became clear that if we were going to reach the 30 gigawatt by 2030 goal, we needed a $7 billion federal investment by 2027. There are not enough vessels in the world right now to install the turbines that we need, not just in the United States. It's not just a Jones Act issue. It is a global vessel and supply chain issue. So this is something we have to think about, and we have to work very closely with our European colleagues on. Next slide. And I just have a few more slides. I think with the delay, this presentation is going a little long. Okay, transmission. What you see in the top right is a macro grid. Imagine 3 superhighways carrying 30 gigawatts each, running north-south, 3 running east-west, from the eastern interconnect to the western interconnect. This is what's going to allow us to share electric power across the country through different time zones and under different weather patterns. You can see that when the macro grid folks got to the East Coast, they couldn't figure out how to put a macro grid in our densely populated North Atlantic corridor, and so they actually put it offshore. And that was independent of the thinking about offshore wind, to my understanding. So these two significant historical currents are flowing together here. And some recent work that we did with Iowa State and Clemson University to try to understand what the macro grid would look like for offshore wind, we developed several different models of the grid, everything from commercial grade 93,000 bus models to reduced coordinated expansion planning models with about 1,000 buses. These buses are sort of individual stations, power stations, and substations on the electric network, and then to a macro grid model. So just a couple more slides of this, and then I'll conclude my presentation. Next slide, please. And so when we look at our commercial grade model, we decided in this effort to wipe the slate clean and to think about what if we could connect offshore wind into the East Coast grid in any way that we wanted to, where would we put it? Where are the points of interconnection that can absorb the most power at gigawatt scale from the ocean and bring them into the grid for the least cost? And so what you see here is a little, what we call this little spur from Deans, Smithburg, and Larrabee in New Jersey, had tremendous capacity to absorb up to about 16 gigawatts of power at a very reasonable cost, all things considered. And so this is an effort to figure out where are the critical points of interconnection on the East Coast and how do we leverage those as we create this offshore wind transmission backbone. And we're going to compare this to what happened in the New Jersey state agreement approach. I'll show that on the next slide. The results that we came up with independently validated what happened in the competitive process of the New Jersey SAA. Next slide, please. Next slide, please. Thank you. These are the results of the New Jersey SAA with the Larrabee tri-collector being rated at almost 5 gigawatts. And you can see by our analyses, there's enough headroom in this area for another 11 gigawatts, provided that you spend the money in expanding the grid and expanding the substations. It's not free headroom, but it's very consistent with the way New Jersey approached this issue. And we're great admirers of the work that New Jersey has done to provide this and to provide these interconnections. And what you see down in that yellow circle is a beachhead that really we need to be thinking about transmission procurement as there's a beachhead and there are procurements in the water and there are procurements on the land. And once you get to the land, these are sort of two issues that are coupled together inextricably, but they can and really ought to be handled independently in terms of procurement and build out. Next slide. And so this is a model where we started to look at different transmission grid designs for 100 gigawatts and for 200 gigawatts. Please move to the next slide. And then this is the model of the macro grid overlay. And you can see, if we go to the next slide, that the macro grid could use the offshore wind transmission backbone as its first corridor. And why is this? This is sort of an unexpected result, but it's because we require subsea cables, HVDC, multi-terminal HVDC technology to build out the offshore wind capacity and this macro grid corridor, which means that we have to create a multi-terminal HVDC supply chain in the United States. Right now, if you want to buy HVDC, you have to wait until the early 2030s. This is an urgent matter of the utmost urgency to build out our supply chain in the United States. And if we build this out on the East Coast and we start to construct this, then we can start to use this technology to build out the rest of the macro grid. Our goal in this case should be to minimize environmental impact by maximizing landing capacities, which means that we have to radically transform the way that we think about individual line capacities to go up above 1.2 gigawatts, up above 2 gigawatts, 5 gigawatts, even 10. And as you know, in the macro grid, we need 30 gigawatt corridors. So how are we going to solve those problems and make the system safe? So thank you very much for your attention. This ends my presentation.
Thank you, Eric. Simon, we'll hand over to you.
Thanks very much, Pauline. And thanks so much, Eric, for your presentation. I think that's touched on a lot of the kind of important aspects that I'll pick up on a few other things, but you'll see that there's some synergy there with the European experience. And like I said, it's very much about scaling up in Europe. How do we get to where we want to be by 2050? And how is R&D helping to meet that challenge? On my backdrop, actually, you can see this is as you cross the North Sea, which I do occasionally to go back to the UK, you can actually see the offshore wind farms in the North Sea between the Netherlands and the UK, and that's one of those wind farms. But at the moment, we still have a relatively small number of turbines in the North Sea, in European waters, certainly in terms of where we need to be in the future. So next slide, please. First point, please. So first of all, I want to talk a little bit about the scale of the challenge and talk about where we need to be and what the targets are. Next. And then I'll move on to looking at the impact in terms of the local wind climate. As you'll see in a moment, the number of wind farms that are proposed to be built out in the North Sea. And I'm taking the North Sea as an example here because that's one of the principal build-out areas for Europe. But you'll see that potentially has an impact in terms of the wind climate. Next point. And of course, the environment's very important. We're building offshore wind farms. We're building renewable energy generation plant to mitigate the damaging effects of climate change on the environment. But at the same time, we want to ensure that the local environment is not adversely affected as well. Next bullet point. Circularity builds on that in terms of we want to ensure that the whole chain is circular, that we can reuse or recycle or reduce as much as possible the amount of material that we use in building the offshore wind farms. Next. Operations and maintenance is a very important area, particularly I mentioned at the beginning, we're moving out to deeper waters and waters further away from the coast. So O&M becomes more and more of a challenge. Next. The turbine technology, it's relatively mature, but there are potentially, looking at the offshore environment, innovations that we could still think about, and I'll touch on that a little bit too. Next. And then finally, the grid. And I think Eric's given a very good perspective from the US in terms of the importance of the grid and how we need to cope with that. And obviously, this is true for Europe as well. Next. So Some of you may be aware that Wind Europe is the main organisation, the main industry organisation in Europe, which represents the interests of the wind energy sector, and they have figures which to show how much, keeping track of how much generation has been installed. Next. And this shows you a map of that. So as of the end of 2023, of course, this is always a moving target, but the cumulative amount of offshore wind throughout the whole of Europe, and the vast majority of that is in the North Sea and to an extent the Baltic Sea, comprises about 34 gigawatts at the present time. The UK is leading the way, followed by Germany and the Netherlands and Denmark. That, as I said, is only a small fraction, as you'll see in a second, of what we actually need. Next. So what about the targets? I mean, it's all about scaling up, making sure that we can reach the targets. And I noticed some of the figures here actually bear some resemblance to the US targets, and I hadn't appreciated that. 2030, we are the aspiration in the North Sea is to have 120 gigawatts, and then by 2050, 300 gigawatts. So that 300 figure is something I saw Eric present before for the US. This is just for the North Sea, of course. There are other targets for other parts of European waters, including Southern Europe, of course. But as I said, the majority of the build out will be in the North Sea. And if we look at what's in the North Sea at the present time, it's about 30 gigawatts, and about, I think, 80% or so of the total offshore installed capacity in Europe is in the North Sea. So we're looking at an increase in the capacity that we have now by a factor of 10 by 2050, so in 26 years' time. And in 6 years' time, we need to have 4 times what we have as of 2023. So you can see what the scale of this challenge is in terms of the build out of offshore wind. Next, please. So what about the impact on the wind climate? Next. This shows you, this isn't a definitive map of where all the wind farms are actually going to be by 2050, but is a plausible scenario as part of a project that TU Delft were involved with called Winds 50, which was to look at the impact from a wind climate point of view of a build out of around 200 and I think it's about 230 or so gigawatts of wind. So a little bit less than the target which has now been suggested, because at the time that this project started, it wasn't quite as high as it is now. But it gives you a good impression of what the scale of the build out looks like. So at 300 gigawatts, you will see more wind farms than that. So the red ones are the existing ones, and the green ones are ones proposed to be built. So you can see a large proportion of the North Sea will see wind farms, and that has impacts potentially on the wind climate. So the impact of one wind farm on another starts to become significant, and also we can understand that that's going to have an impact on bird migration across the sea, certainly between the UK and continental Europe, and that's a concern in terms of potential bird strikes, and something that certainly the Netherlands is very concerned about, ensuring that we don't in the build out wind farms we don't have a huge impact in terms of bird migration, birds avoiding the wind farms, as well as birds being hit by the turbines, because avoiding the wind farms means they have to go around them. And of course, that has implications for the amount of energy they expend, and that can have an impact on their breeding. So that's an area that requires further research. Next slide. So the Winds 50 project used some code developed by Wiffle, a spin out from the university, TU Delft actually, to look at the impact on the wind conditions. So this shows you just a snapshot of the wakes, effectively the wakes that are produced by the turbines at a particular moment in time. And you can see how those wakes persist. And of course, if you're building a wind farm, you need to ensure that you take into account your neighbours if you want to do a proper assessment of the energy yield. If you don't do that, then you can be out by quite a few percent probably 5 to 7% on average. Some wind farms more, some wind farms less. This still requires, I think, further work, and this is perhaps one of the first studies to look at that, but it does show that this potentially, the cluster effect, it can be quite significant. Next. Just to show you, that was in a simulation. This is an actual image of, so this is what happens in reality here. So this is a satellite image where microwave radiation effectively reflecting, bouncing off the sea surface is used to infer the 10-meter wind speed. Because the windier it is, the rougher the sea surface is, so the larger the radar reflection is. And you can see the color is the wind speed. So the green, the light blue, higher wind speeds, dark blue, lower wind speeds, and you can see what's circled there is perhaps one of the largest at present time clusters of offshore wind farms, the Belgian-Dutch cluster. Part of that is very dense, and you can see the impact it has on the wind conditions. The wind is coming from the southwest here, and you can see it has quite an impact, and that's where we are today. So this effect is real. So it's something we have to get a good handle on if we want to ensure that we get a proper estimate of the yield of our future wind farms. Next. One of the ways we can try and improve the output of the wind farms is to reduce the wake losses, so the impact that one wind turbine has on turbines further downstream. So this is an example of that. On the left-hand side is what would be considered the normal situation, where each turbine is operated under what they call greedy control conditions, where each individual turbine maximizes its output depending on the wind speed that it sees. The second one is where the first turbine, the blades are pitched, they're pulsed, so that it pitches very, very, very rapidly to induce turbulence, extra turbulence, and that helps to mix out, if you like, the effect of the wake. So it mixes in the faster moving air from outside the wake, and potentially for a row of turbines can reduce the losses. And then on the right hand side is an example where the blades are pitched cyclically, and that creates a rotation of the flow, which again, that rotation helps to mix out the effect of the wakes, mix in the faster moving air and reduce the wake losses. So there's a lot of interest in terms of using smart control of the turbines to try and improve the energy yield, the efficiency of the wind farm. And that's something we're going to have to think more and more about as we build more and more wind farms. Actually, realizing this for large arrays of wind turbines needs to be, that further research is required. Next. So the environment, as I said, that's important, of course, that where we want to reduce CO2 emissions, we want to try and mitigate the impacts of climate change, but at the same time, we don't want to have a big impact on the local environment. Next. And one of the things we need to consider is that still the vast majority of the wind turbines which are installed in the North Sea, installed in shallow waters, and they use monopiles. And if you hammer in these things, then it's very intrusive in terms of the noise that's created. And some of these monopiles are getting pretty big now. We're looking at diameters of maybe 15 meters and depths of over 120, lengths of over 120 meters. And that's huge for the largest monopiles, which are certainly going to go in as we build more and more wind farms. So instead of hammering them in, which is the normal way of doing it, you basically have a big hammer and it whacks the thing in. One way of reducing the impact is to actually twist it back and forth relatively rapidly. That's much less intrusive. It reduces the noise much significantly, and also they're going more easily as well and can be extracted in the same way. And that has implications because it reduces the noise which is experienced by marine mammals in particular, and fish also, which is important when we're installing wind farms. Next. So circularity, we want to ensure circularity, and blades is perhaps one of the biggest issues here. Recycling the towers and the components in the nacelle is perhaps less of a challenge, where we're used to recycling some of those things, but the composite materials in the blades represent a challenge. Next, please. So we need to rethink things like how we manufacture them and the materials we use. Next. So this is obviously very Dutch, a saddle from a bike, but this is using flax, and flax has a much smaller environmental footprint than things like carbon or glass fiber reinforced epoxy. So we can think about using materials such as flax to make the blades more sustainable. Next. And also the way we manufacture them, we can think about using techniques which are less energy intensive, and we've been looking in the university in terms of using tapes and sintering the tapes in place using lasers to allow the construction of the blade. Next. Another area of interest is actually making the blades reusable, so using thermoplastic materials rather than thermoset. So you can actually you can press them in the first instance, which is what we're showing on the top, and then next. And at the end of life, you can then use that material, put it in an oven, and then recover the laminate. So actually, ours is to reuse the material as opposed to what we tend to do nowadays, which is cut the blades up and bury them, which isn't terribly sustainable or circular. Next. And here's an example here of a blade that's been made using thermoplastic composites. Next. So O&M, particularly as we go further away from shore, is quite a significant fraction of the cost. And we need to think about being more proactive, more predictive, and be able to make accurate estimates of remaining useful life from limited number of observations that we can make of the blades. Next. And one of the projects we're involved with is something called Holy Doctor. So we're looking at an offshore wind turbine, and then next, how we can use information, firstly, from the drivetrain, which actually is a rich source of information, not only to understand how the drivetrain is behaving, but potentially how the rotor is behaving, because vibrations through imbalance on the blades due to maybe damage can manifest itself in terms of vibrations on the drivetrain. So we're looking at drivetrain modeling next, and then also a combination of techniques next to actually make measurements on the blade. So not just in Delft, but in other institutes in Europe, the use of infrared is being used to look at internal damage on the blade. Next. Vibrometry, so looking at how the blade behaves in terms of its motion, can be a useful indicator of its state of health. Next. And something that we've been experimenting with is looking at the aeroacoustic signature, so the noise the blade makes. So if you can imagine the blade is delaminating, it changes its shape, and that changes its aerodynamics and potentially its aeroacoustic emissions. So we're looking at using the aeroacoustic signature to detect certain types of damage. Next. And then how that can be used holistically, and of course AI comes in everywhere, but it for this sort of application is very useful. You can bring together different techniques to give you a more holistic impression of the state of health of the blade. Next. Which then can be used for fault detection, diagnosis, and prognosis. Next. To help with using other supporting data. Next. An O&M model. So that's very important, of course, using modeling operations and maintenance and when to send boats out. Still, there's a lot of work to understand the best way of doing that and the logistics, how we can optimize the logistics of that. Next. To minimize LCOE and optimize scheduling. Next. And of course, all of that can be used to try and increase the circularity of blades and minimize their impact on the environment by increasing their lifetime potentially, but also it can be used as a way of engaging the public as well. That's something we're looking at in terms of how O&M is being used in the industry to make wind energy more circular. Next. Okay, next slide. So the technology, of course, we think the turbines are quite mature, and we're used to the three-bladed upwind wind turbine, the so-called Danish model, but there are other options, of course. Next. And if we look at the different offshore technologies, we've got the bottom fixed monopile turbine, which is, as I say, certainly for Europe has been the most dominant design. But there are moves in some of the deeper waters. Although the North Sea is mainly shallow, there are some areas you start to go north which become deeper. And of course, in the south, in the Mediterranean, then you are in deeper waters quite quickly. And of course, in the US, as Eric showed, as you get the continental shelf is quite short as you go out from the east coast, so you're into deeper waters there quite quickly too. So looking at floating becomes more and more important. Now, I've shown an example there of you can see an airborne wind energy device, which is something we're looking at, which is probably quite somewhere in the future yet. Next. So floating renewables is something that we are quite actively working on here in Europe and certainly in Delft, and we're looking at ways, testing facilities to improve the platforms and improve the turbines, and we're looking at using hybrid testing, so using different facilities. The challenge with floating is that you've got different, if you're trying to do this at scale in the lab, things don't scale up in the same way above and below the water, so that represents a challenge, and we have multiple facilities across the university that can be used in a complementary fashion to allow us to do hybrid testing to get around these scaling issues. But that's an area I think that's increasingly important if we want to move to deeper waters. Next. This is a concept that we've been looking at with other colleagues around Europe, which is it's using a vertical axis design, but the power takeoff is not through the main shaft of the rotor as you would expect from a vertical axis turbine, but it has very small rotors at the bottom of the design here, which is a sort of X design, and there's smaller rotors at the bottom where the power takeoff. So they're small rotors running at high speed, and there are multiple benefits of such a design in terms of weight and cost and the ability to do away without the gearbox without having a gearbox, for example. Still very relatively low TRL, but we have demonstrated the concept at least on paper, and there is interest in an actual physical scale demonstrator, and that's something we hope to be involved with. Next. So finally, just a few words on the grid, and Eric's said quite a lot about that, but it is, of course, important for Europe. Next. And we, along with many other colleagues across Europe, are looking at what the issues are, and we have facilities to do that. So we have an electrical sustainable power lab in TU Delft, and we're looking at a number of different issues here. We're looking at detailed models of the grid in terms of how we can ensure grid stability. We're looking at new materials for the development of some of the components to make them more circular, for example. We're looking at how we can manage the dynamics where you've got a large amount of renewables on the grid. We're looking at how we can manage curtailment, which is still something which it has to be done in terms of managing the amount of power that has to come from the wind farms to the European grid. Of course, at the moment, all of our offshore wind farms are point to point, so that will have to change in the future. We're looking at a pan-European offshore grid, and that comes with its own challenges in terms of stability and cross-border trading, of course. Standardization of components is important, and that's something that we're looking at too. And some of the ancillary services that are going to be required, so synthetic inertia, grid forming, black start. So we're looking at all of those things there and how they can, in the future, where we've got a large amount of renewable energy, not just offshore wind, but other renewables, particularly PV as well, how those all come together. So that's an area, obviously, of a lot of active research in Delft and elsewhere. Okay. I think that's my presentation finished. Pauline?
Thank you very much, both of you, for those fantastic presentation. We have a few questions. We're going to try to cover certain of them. I'm not sure we have a lot of time, but we're going to try anyway. Eric, this would be for you. What is your view? What is the relationship between state and federal entities in the realm of research, and what should it be?
I think that the states and the feds in the US are working on more collaboration. I think that the issues that we're dealing with are regional. We have, in the early history, there was an attempt to every state, understandably so, wanted to get all the supply chain, within its own borders and create its jobs. But again, the question of scale comes up, and when you start to understand that, and people are really understanding the need to cooperate regionally, especially when it comes to the grid and all of these things. So I think the forward movement there is the name of the game is how do we collaborate more effectively.
I think, Pauline, just to add to that, the analog in Europe, of course, is there are the national governments. They all have their targets, and they're all building out the wind farms. But the European Union is very keen to, that the countries collaborate here. That we have to, because of course the North Sea. Eric says it's quite big, but actually it'll get quite crowded. And of course it's multi-use. It's one of the busiest areas, in terms of traffic movements across in the world. And there's a lot of R&D that goes into funding cross, trans-European projects, and we're involved in some of those. And that's very important that we all share our experiences and that we all collaborate to ensure that the system works for everybody.
Thank you. Would you describe what is your view on the various scales of research, from individual investigator to large teams or major research infrastructure investment, and how do you see they contribute to the research ecosystem altogether?
Who's picking that one up? Eric?
I'll start. I think, again, we have this issue of scale, and we have the issue that you have a system of systems, which is complex and which requires expertise from multiple domains. This makes it very hard for an individual investigator to make progress in isolation. And yet a lot of the research culture is focused on individual achievements. And so I think for a long time, I know in the US, we've been considering how do you do large scale team research? And one has to approach it in such a way that we really focus on making sure that teams are able to work together, that they're able to be effective, that they're able to be inclusive, and that they're able to interface with other sectors in society. So I think the assets that we need, and clearly the assets that Simon is talking about at TU Delft, are they're just fantastic to behold, and we're great admirers of them. These are not cheap things to build. You have to invest a lot of money, which means then you have to cooperate and you have to share them. So I think this is really where this is headed, and how do we plug individual work into larger research frameworks is an area at the cutting edge of research and development.
Yeah, I mean, collaboration is the name of the game. I mean, there are certain things you can do at the small scale level. I mean, I give that example of the WINS 50 project. One of the partners there is actually spin out from the University of Wiffle. So they're still, well, actually, they're becoming quite a sizable company now. But, they've done a lot of work on developing fast models for prediction of wind speed and power and performance of wind farms in not just offshore, actually onshore, but also for forecasting power output and forecasting resource. So that's just one part of the puzzle. But of course, then how that links in to, like I said, impacts on birds, impacts on the grid. Then you start to bring in all these other players. So there is a place for the smaller players like Wiffle, like the companies that develop the drones, for example, and some of those are spin outs from the university. And then obviously, but you do need to bring that all together because it is so multidisciplinary in environment, aerodynamics, civil engineering, electrical engineering, markets, of course, social impacts, and also, of course, the wider sort of, public buy-in to this as well, and the impact it has on the price of energy and the affordability of energy. So there's a place, I think, for the individual smaller players, but also, yeah, we need to think quite big in terms of how these consortia can actually solve these big problems, which, as Eric says, are systems of systems problems.
Thank you. We're running a little bit out of time, but we have a question that we would like to ask you. What do you see? What are the biggest barriers to move from research into the market? Simon, maybe first.
Biggest barriers, I suppose it's a case of I mean, often the larger developers, they're quite conservative in terms of the technology that they use. It has to be, tried and trusted. So often there is this hurdle that has to be overcome in terms of, showing that new innovations actually make sense from a commercial viewpoint. So that's probably one of the biggest hurdles, I think, that persuading people that what we're doing actually is important to consider in their future build out. And the Netherlands has been quite progressive in that, perhaps unfortunately not so much in the latest rounds, but in terms of ensuring that when consortia come together to build or to tender to build offshore wind farms, that they have a degree of innovation in their bids, and those innovation activities can only happen with R&D, with research institutes. So yeah, I think overcoming that kind of conservativeness is probably one of the biggest barriers.
Thank you, Simon. Eric, would you have a word on that? And after we're going to wrap up.
I would say opportunities for demonstration and demonstration at scale. And even though these demonstrations cost, they cost a lot of money, the amount of money one would spend on them in comparison with the amount of money we're spending on the build outs is extremely small. So I think we have to think about large scale demonstrations, which is what we've done in other areas of infrastructure development throughout history.
Well, thank you very much. I would like to thank both of you very much for your enlightening us with those major changes ahead of us, and well, explaining how you are both on the forefront of those issues. Thank you very much. Thanks for all of you for joining us for this learning from the expert webinar. So a reminder: the webinar is recorded, and recording and presentation will be available on NYSERDA's website shortly. Our next webinar will be on May 29th. The National Offshore Wind Research and Development Consortium will discuss innovation and emerging technologies in offshore wind. And on June 12th, the New York Independent System Operator will present on how offshore wind connects to the New York electric grid. You can register for future webinars through our events page. And we also encourage you to check out past webinars in the series on the website and YouTube channel. If you have requests for future topics that you would like to have in the series, please email us or fill out our Learning from the Experts survey posted on our website. Thank you for joining us today. See you next time. Thank you.